This is the last problem we looked at last time from section 4.5. Section 4.5 is about U substitution, but this problem in particular, we can't do with U substitution. So section 4.5 ends with some, alternate techniques of calculating integrals. One of them involves using geometry. So here, we'll just very quickly remind you how this problem goes. Here we're given this definite integral. And here, no U substitution is going to work. If we let U equal 9 minus x squared, then du is minus 2x dx, and we don't have any x dx. So in this case, the trick is to kind of interpret the picture of the integral. And here, the integrand, positive square root of 9 minus x squared, is this upper semicircle. And so when we look at the picture, we realize, oh, well, this area problem, we don't need an integral to solve. We can solve this using our formulas from geometry for the area of a circle. And so in this case, it's a half circle, so we divide by 2. And so just by using our formulas from geometry, we're able to get an answer. So in this problem, we never actually did any integration. We still don't know what the antiderivative of the square root of 9 minus x squared is in this case. So here, previously we motivated the definite integral by saying, oh, I've got a function and I'm trying to find the area under the function. Let's use the integral to figure that out. And here we've done exactly the opposite. I've got a definite integral. Let me calculate the area under the function to find the definite integral using formulas from geometry. And so this is the last example of section 4.5. It's a little bit tricky. I wanted to give you a slightly tricky problem. So here, first we notice it's a definite integral. It's an integration problem. It's not, the integrand isn't something we know how to integrate just off the top of our head, so we have to try some technique. And so here, one technique is to try U substitution. And we notice if we try a traditional U, like for example, if I let 9 minus x to the 4th be U, then du is going to be minus 4x cubed dx. And the minus 4 part isn't a problem because you say, oh, I don't have a minus 4. The real problem is the x cubed dx part. Because outside in my integrand, I have an x, I do not have an x cubed. And that's a problem. I can't just multiply in an x squared and divide by x squared. We can't do that with variables. We can do that with constants. So here, this is not necessarily, this is not an easy problem. Eventually when we think about it, we think about that, well, x, that would come out if you took the derivative of x squared. Like the derivative, if u was x squared, then du would be 2x dx. And we wouldn't have the 2, but we'd certainly have the x dx part. And so maybe that's helpful. So here, that's what we try. So we try, after some trial and error, we think, okay, let's try u equal to x squared. Then that gives us du equals 2x dx. And we don't have the 2, that's okay, because I can multiply and divide by 2. What's important is that we do have this x. We see x dx in the integrand, we have an x dx. So maybe this will work, let's see. The other thing is this is a definite integral, so I convert the bounds. So when x equals 0, using this equation, using the original substitution u equal to x squared, we see u equals 0. And similarly here, when x equals the positive square root of 3, u equals root 3 squared, or just 3. So okay, let's convert the integral and see what happens. So first I'm going to write the x to the 4th term. I'm going to write that as x squared squared. Why? Because I want the x squared is my u sub. I'm going to replace the x squared with u. That's exactly the u sub that we're doing. And the 2x dx, so here I multiplied by a 2, and I also divided by a 2. And the reason I did that is now I have the 2x dx, and the 2x dx will become my du. Yeah, so I'm ready to change from the x variable to the u variable. So you can see we have the 1/2 from when I multiplied it in. The 2x dx becomes a du because 2x dx equals du. The x squared here, I replaced with u, and that was x squared squared, so that becomes a u squared. And finally, the bounds. I changed from bounds in the x variable to bounds in the u variable, again, coming from the substitution. So now when we look at this new integral, again, it's not one we could do with the U substitution, but it is very similar to the type of problem we just did on the previous slide. If we graph this thing, we could do this geometrically. Once we realize that this root of 9 minus u squared is the graph of a semicircle. In general, the graph of plus minus square root of like any constant minus x squared, that'll be the top and bottom of a circle. So here we're taking the positive root. So here it's the top half of the circle, but if you look at the domain goes from 0 to 3. So it's not the entire circle, right? So the entire circle would go all the way down to here, and we go -3 to 3, but we're integrating from 0 to 3. So in this case, we're only trying to find the area now. This definite integral is now trying to find the area of this quarter circle. And again, we say, oh, we don't need calculus to find the area of a quarter circle. We have a formula from geometry. So here I'm doing pi r squared divided by 4 to find the area of the quarter circle, and then the 1/2 from that was in the front from trying to get the du. I just copy that. And so then we do the algebra and we're able to solve the problem. And again, here it's important to realize we didn't actually ever find an antiderivative. Here we never used fundamental theorem of calculus part 2. Instead, we interpreted, in this case, we first did a U substitution and then interpreted that resulting definite integral geometrically. So we've really, have ended by completely doing the integrals, doing the opposite problem, finding the area using geometry to evaluate the definite integral. And at the beginning, we were doing quite the opposite. So this ends our discussion on section 4.5. And so now I start the very last chapter of Calc 1, which is chapter 5. Calc 2 will go through chapters 6 through 9, and I believe Calc 3 is chapters 10 through 13, something like that. So you'll go through the entire book. So we talk about inverse functions. So first question to ask is, why are we talking about inverse functions? This is a topic we've covered in pre-calculus. So chapter 5 is all about the natural log function. In section 5.2, we will introduce and formally define the natural log function. And then we will immediately be interested in the inverse of the natural log function, which is the exponential function. And so that's why we're talking about inverse functions. We will eventually be interested in the inverse of the natural log function. So first, a preliminary definition. A function is said to be one-to-one, or we write 1-1 here, one-to-one, if and only if x sub 1 not equal to x sub 2 implies f of x sub 1 does not equal f of x sub 2. So let's interpret this, not mathematically, but let's interpret that qualitatively. It's saying the function f of x is one-to-one if and only if you pick two different inputs, plug it into the function, and you get two different outputs. It's not always true that if you plug in two different inputs into a function, you'll get two different outputs. For example, look at the function y equal to x squared with unrestricted domain. For example, if I pick x sub 1 to be -2 and pick x sub 2 to be 2, those are my two different inputs. -2 does not equal -1. But the output, when I plug it into the function, they both get sent to 4, right? When I plug in 2 into the function, it gets sent up to 4. When I plug in -2 into the function, it also gets sent to 4. So here, this function is not one-to-one. For inputs that are different, that doesn't guarantee the outputs will be different. And if you compare it to the graph here on the right, which is x cubed, y equal to x cubed, this function is one-to-one. Here you can pick any input, go up to the function, find the output, it'll always be unique. There will never be any other input that will go to that output. Pick any input, find the corresponding output, that output will be unique. That is to say, there's no other input for this function that'll give you that specific output. And so a graphical test for that is called the horizontal line test. So if any horizontal line drawn through the function, intersects the function more than once, then the function will not be one-to-one. So here for x cubed, any horizontal line I draw, assuming these are horizontal lines, will at most cross it once. If it at most crosses it once, then it is one-to-one. And why do we care about one-to-one? Because in a moment, we're going to reverse the input-output relationship. In a moment, I'm going to ask, is it possible for me to treat the range elements as the inputs and the domain elements as the outputs? In this case, with the function x squared, it's not possible. Here, if I pick this number here as my input and then try to use the function to find an output, in this case, for example, if that was the range value 4, in this case, we know for the function y equal to x squared, there's two possible inputs that'll give you the output of 4. So in the case of a function that's not one-to-one, it's not possible to reverse the input-output relationship. However, for the function that is one-to-one, like for x cubed, you can pick any number in the range and go backwards, follow the function to the domain element. You're always only going to get sent back to one possible element in the domain. There's no way two domain elements will map to the one range element. That's just not possible for a one-to-one function. So the moral of the story is here that one-to-one functions have inverses. That is, we can reverse the input-output relationship, but functions that are not one-to-one, we cannot reverse the input-output relationship. So remember the definition, and that's because of the definition of a function. A function specifically is an input-output relationship in which for each input, there's only one output. And so you see for a one-to-one function here, if I try to reverse, for a function that's not one-to-one, if we try to reverse the relationship, we don't get that unique, output for each input. You can see here, for x squared, actually, any range element actually has two inputs that map to it. So here, we can't just reverse the function reverse the relationship for a function that's not one-to-one. So how do we create the new input-output relationships? I want to now create a new input-output relationship that we're going to call the inverse function. Basically, we're going to just reverse the relationships that the original function f of x gives us. That is to say, if f of a equals b, so let me read that another way. If for input a, I have output b, then now let me define this new function where for input B, I have output A. So another way to define that function is to say, if f of A equals B, then define g of B to equal A. G will always, undo whatever f does. If f of smiley face equals sad face, then g of sad face equals smiley face. It'll always reverse the input-output relationship. So we can interpret g as the inverse, or we can interpret it as the solution of the equation f of A equal to B. If we're trying to solve f of A equal to B for A, then you can see here that A would equal g of B, the inverse. So anytime we're solving an equation, we're actually inverting it and basically finding the inverse to solve it. That's why the concept of inverses is really important. We're always essentially inverting something when we're solving an equation. That is something with an equal symbol, an equation. So here's the official math definition. We say f and g are inverses of each other if and only if f composed with g equal to x. So the way I interpret this is the function g does something to x. And now f undoes whatever g did to x, and it gives us back the original input x. So x was altered by g, and then f basically unaltered g of x to give us back the original x. For example, if g of x is the function where you add 2, like g of x equals x plus 2, then f would be the function where you subtract 2. If g of x were the function where you're multiplying by 2, then f would be the function where you're dividing by 2. F undoes whatever g does. And it's not a mysterious definition. It all comes from right here. Here, this equation says a equals g of b. So if I plug in g of b for a right here, that says f of g of b equals b. It's basically exactly the same as this statement. And the other part of the definition is that g undoes whatever f does. So g composed with f of x is equal to x. Again, we can look at this definition here to get that formula. Here, b equals f of a. So if I take f of a and plug it in right here, I get g of f of a equals a, which is exactly this statement right here. So, when we bring the composition into it, it kind of looks complicated, but at the end of the day, all we are doing is reversing the input-output relationships. If I have a function that's one-to-one, and if I know f of a equals b, then I can immediately tell you g of b equals a, even without knowing a formula for g. All I need to know is how does f behave, and then reverse the relationship. So some notation here, the inverse is denoted with this notation. It's an f. So for example, the inverse of f would be the letter f with a -1 in the superscript position. Okay, so that's pronounced as f inverse. So that's pronounced as the f inverse of x, and is known as the inverse of f. So that would be f inverse of x, and it's defined to be the inverse of f, and we know by definition that f composed with f inverse of x equals x, and f inverse of f of x equals x, because they undo each other. Be careful, this is not a reciprocal, okay? So here, this is not the same. I'm going to put a not equal to, and I'm going to put a big parentheses here, do an f of x, put another parentheses, and put a -1 on the outside. This is, the inverse is not the same as the reciprocal. Be careful with your notation. And I'll mention this point again. Look at where the inverse is. If the inverse is right on the f, If this -1 is right on the f, that's an inverse. If it's not directly on the f, it's a reciprocal. So as I mentioned, a function has an inverse if and only if it's one-to-one. This is because for every input, we need a unique output, and only one-to-one functions have this property where you can reverse it. The graph of f inverse is just the graph of f of x reflected about the line y equal to x. I mean, we're literally saying if a comma b is on the graph of f, then by definition, the opposite b comma a will be on the graph of the inverse. So we're literally just, reversing it. So here, if this point, a comma b, so I go out on the x-axis, that's the distance of a. On the y-axis here, this is the height of b. Literally, we're going to reverse that. Literally now, on the y-axis, this is a height of a. And on the x-axis, this has gone out a distance of b. We've literally reversed our relationships here of input and output. And the result in the graph is we're just basically flipping about the diagonal. We're making x equal to, so that's a, and this is the original b, and now they're flipped. So now I have, here's a, here's b now, and here's a. It's completely flipped. So yeah, by reflecting around the diagonal line, we can find the graph of the inverse. Similarly here, the relationship of domain and range change. If this is the domain of the original function f, now that reflects onto the y-axis, and that becomes the range of the inverse. And vice versa. The range of the original function f, which is right here, this would be the range here, becomes the domain of the inverse. Again, this is from switching the x's and y's. Here's the most important equation I can tell you when it comes to working with inverses. That if y equals, to write this, if we write y equals f inverse of x, we're also saying this is the same as saying f of y equals x. And it's really important, and I'll mention this many, many times, and it's very important we understand how to get from one equation to the other. So if I want to go from left to right, apply the function f to both sides here. So here, let me just make myself some room here. So yeah, if I want to go from left to right, what you should do now is take f of both sides. So here do f of y equals, and on the other side do f of f inverse. And well, f of y just gives me exactly what I have here, f of y. And here, look, f of f inverse of x, the f undoes whatever f inverse does and just returns the original input x. So by applying f to both sides, we can go from the left-hand side to the right-hand side. So here, apply f to both sides. How do we go from the left-hand side to the right-hand side? So there, let me show you, let me make some room here. So now if I want to go the opposite direction from f of y equal to x to y equal to f inverse, here, apply f inverse to both sides. So here, I'm going to do f inverse. So look here, I take f inverse of f of y, and here I'm taking f of x. You can see on this f of x is just, sorry, f inverse, sorry, I'm taking f inverses on both sides, oops. So this should be an inverse here too. Okay, I'm doing f inverses on both sides. So you can see the f inverse of x is just what we have here, f inverse of x. And here, f inverse of f of y, they cancel out, and we get back the original y. Okay, so it's really important that when you look at this equation, you understand how to get from what's written on the left-hand side, this equation right here, and how we get to this equation here, and vice versa. From fy equal to x, how do I get to y equal to f inverse of x? You know, and I'll go over this a whole bunch of times. This is one of the fundamental ways we work with the inverse function, by changing the problem. We'll be given y equals f inverse of x, and we'll rewrite the problem as f of y equal to x, and do our math here with this equation. Okay, so that's going to be a standard strategy which we'll go over and over again. And of course, let me remind you again the notation that in general, it's not true that the inverse of a function is its reciprocal. So here's the algorithm for finding the inverse. It's quite unrealistic because in general, it's not very easy to solve, to do this first step. The first step is we want to solve the equation y equal to f of x for x. In general, that's not going to be easy. Once we've solved for x, then we want to interchange the symbols x and y. At this point, whatever you have equal to y is the inverse of f. So whatever y is equal to, that function is the inverse. I'll show you an example here in 1 second. Finally, we can check. You can check that f inverse of f of x equals x and f of f inverse of x equals x. Usually, if one of them works, then the other will work also. So typically, we only check one of them, but you don't have, you know, technically we should check two, but typically we only check one of them. As I said, in general, this is, you know, very unrealistic. It's not in general feasible to solve the equation y equal to f of x for x. That only works in the nicest cases. However, in theory, given a function, given a one-to-one function, we can always theoretically define the inverse. If I know f of a equals b, then without knowing the formula for the inverse, I know f inverse of b equals a. I can always define f inverse by reversing, you know, how f behaves. So I don't need to actually explicitly know the formula of f inverse. If I know how f behaves, then in theory, I can reverse that behavior, and I know the inputs and outputs for f inverse. So here I say, you know, we can define it implicitly. That is, I can define f inverse of x to be equal to y if and only if x equals f of y. You know, and so this is a way of using the original function to define the inverse without ever actually finding a formula for the inverse, just by reversing the relationships. So there's a theorem on the continuity of the inverse. If f of x is continuous, and of course one-to-one, then its inverse will also be continuous. And of course, one-to-one, since it has an inverse. So here's an example where we're asked to find the inverse. And here I wanted to do an example that's a little bit tricky. So first of all, what I'm going to do in this example is just to check that the function's one-to-one. Certainly, you don't have to do that. If the book is asking us to find an inverse, then we assume the function is invertible. We are able to invert it. So that might be a new word, invertible. Here, just for giving you a mathematically complete presentation, I want to show you that this function is one-to-one. Here, I call the function y, it's x squared minus 2x plus 1. Here we can factor it. So I write as x minus 1 squared. And don't forget, here we have a domain restriction that x has to be greater than or equal to 1. So here the graph looks like, you know, this right-hand side of this parabola. Without the domain restriction, we'd have this other side of the parabola. I don't know if it's going through one. We'd have the other side of the parabola here. But with the domain restriction, we don't have that. And with the domain restriction, this parabola now passes the horizontal line test and is one-to-one. And so it does make sense to ask, what's the inverse? So now let me solve the equation y equal to x minus 1 squared. Let me solve that for x. Now, in the slides I sent you, you might have a typo. You probably do have a typo. I accidentally put the plus minus on the wrong side in the slides that I sent you. The slides I sent you have a plus minus on the x. And so it's actually incorrect. It should be on the y. So let me show you how that works. So suppose I have an equation like x squared equals a. The proper way to solve this is we bring the a over. So write this as x squared minus a equals 0. And then factor this as a difference of squares. I factor this as x minus root a times x plus root a. And they're both equal to 0. And so now the only way this is possible, so now from this first root, we get x equals root a, or as x is equal to plus root a. And from this second equation, we get x equals negative root a. So that's how you get the plus minus when you have an equation like this, x squared equals a. Here, I don't have x squared, but I have x minus 1 squared equals y. So this is like x tilde squared equals a. So x tilde equals plus minus a, and then you move the 1 over to eventually solve for x. So that's what I do here. Okay, so watch out, that plus minus I put in the wrong place. It should go in front of the y term. Another way to think about this is if you square plus root y, you'll get y. If you square x minus 1, obviously you get x minus 1 squared. If you squared minus root y, you'll get back y. Obviously, if I square x minus 1, yeah. So no matter what, if you square plus minus y, I always get y here. And if I square x minus 1, I always get x minus y squared. So I'm looking for all the roots that'll satisfy this equation. So both the positive and the negative root, i.e. the square root of y. Anywho, now that I've solved, here's one reason why I wanted to do this example. We actually have two answers here. So if you look here, we get x is either equal to 1 plus root y, or it's equal to 1 minus root y. So here's why I did this problem. Is I want you to think about, okay, how do we eliminate one of these answers? And here's where we look at restrictions, So for example, the domain restriction says x has to always be greater than or equal to 1. Here, 1 minus root y, that's actually going to be less than or equal to 1 because you're subtracting, root y. Here, 1 plus root y, yeah, that's going to be greater than or equal to 1. So that's the answer we keep. And this is part of the reason I wanted to do this example, to where you have to think about, okay, there's two answers, which one do we choose? And so now I interchange the variables. So now x equal to 1 plus root y becomes y equals 1 plus root x. And so this function here that's set equal to y, that's our inverse. F inverse equals 1 plus root x. And I say here x has to be greater than or equal to 0. You can get the domain, if you look at the range of the original function, is exactly, y has to be greater than or equal to 0, and the range of the original function becomes the domain of the inverse. So that's one way to think about it if you want here. And so here we can sketch the graph, draw a diagonal line, and then reflect the function about the diagonal line. And so you get the graph of the inverse. Another problem really quick here. So again, here I sketch the graph. So one thing with this is if you let x equal 0, y is equal to 1. So if I let x equal 0, y is equal to 1. And the denominator is bigger than 1 because it's 1 plus x squared, and x squared could be greater than or equal to 0. So the denominator is greater than or equal to the numerator. So this fraction is always less than 1. And as x goes to infinity, the function will go to 0 by dominance of powers, but it always stays positive. So the function kind of has this type of bell shape. And here we have a domain restriction. We are excluding this entire, left side because x has to be greater than or equal to 0. So when I graph the function very roughly, just by plugging in points and taking some intercepts, I get that, and then applying the domain restriction, of course, I get that the resulting function is 1 to 1. It passes the horizontal line test. And so here, I can now try and find the inverse. So y equals 1 plus x squared. I took a reciprocal of both sides. So I get 1 over y equals 1 plus x squared. And then I moved the 1 to the other side because I'm trying to solve for x here. So I get x squared equals 1 over y minus 1. And now x equals plus minus 1 over y minus 1. Again, there are two answers here, a positive root and a negative root. And here I can use the domain restriction, which says x has to be greater than or equal to 0 to eliminate the negative root. And finally, if I interchange the symbols, we get our inverse function. So whatever y equals here is our inverse. So the inverse here is 1 over positive square root of 1 over root x. Positive square root of 1 over x minus 1, excuse me. And we can graph this using the original graph, draw a diagonal line, and then fold the paper along that diagonal line and reflect the graph. So that takes a little practice sometimes, reflecting the graph. So you should play around with that. So our final result here for section 5.1 is we have this theorem about finding the derivative of the inverse without actually differentiating the inverse. That's what I want you to appreciate about this theorem. So we start with a one-to-one function. Of course, it has to be one-to-one so that it has an inverse. And differentiable. Of course, it has to be differentiable to have a derivative. So now what we want to ask, what we want to find out is for the inverse function, if you give me some point A in the domain of the inverse function. So here, suppose f of c equal to A. So A here would be in the domain of the inverse function, right? So remember, f of c equal to A, that's, so take f inverse of both sides. Take f inverse of f and take f inverse of A. Okay, so A is a function that's in the domain of the inverse. What I would like is a formula to find, very carefully now, the derivative of the inverse function at this point A. So first, make sure you understand what the left-hand side is asking for. We don't know what it's equal to yet, but just figure out, make sure you understand what we're looking for. We're looking for a derivative of which function, the inverse function, at which point, this point A. So here's what the theorem tells us the answer is. Ignore this middle part for a second. Actually, let's just go to this end part. So here, I'm going to ask you to just, for 1 second here, ignore this stuff. So it says the derivative of the inverse at A. So now let's really make sure we understand the left-hand side, okay? I mean, the right-hand side. So we're going to take a reciprocal of the derivative of f. That's 1 over f prime. We have not differentiated the inverse. That's 1 over f prime. And then evaluate that derivative at the number c. Here's the important part. C is not random. C and A are connected, right? C and A here are related through this equation up here. Don't forget here that C equals F inverse of A or F of C equal to A, however you want to think about it. So A and C are connected. They're not two random numbers. They're related. They're inputs and outputs, depending on which function you look at. So to find the derivative of the inverse at A, I look at 1 over the derivative of F at C. Okay, so first I just want you to understand what it's saying, and then we'll figure out why this is true. We'll do the proof in a second. And here the expression in the middle is saying exactly the same thing, okay? So here is my reciprocal of the derivative of f. And here, f inverse of a is just another way of writing c. If you look up here, f inverse of a and c are the same thing. Okay, so the notation can look a little confusing. And of course, we require the denominator not to be equal to 0. And here, what you should really appreciate is that we're finding the derivative of the inverse on the left-hand side, derivative of the inverse, by finding f prime and by solving this, and by finding the number c, which involves solving this equation f of c equal to a. So we're able to find the derivative of the inverse without actually finding an inverse and without actually differentiating the inverse. That's what's nice about this theorem. It's a shortcut to finding the derivative of the inverse without actually differentiating or finding the inverse. It's important you understand why we're even studying this theorem or care about it. So here's the proof. It's not difficult. The proof just uses implicit differentiation or chain rule. So starting from y equal to f inverse of x, I rewrite the equation, and you remember how we do this. Apply f to both sides. F of y is exactly f of y right here, and f of f inverse of x just gives me x. Now we're going to differentiate, but remember y is a function of x. So f of y is a composition of functions of x. So when I differentiate with respect to x, I need a chain rule. So here I have, this is the derivative of the outside evaluated at the inside times the derivative of the inside. On the other side, the derivative of x, of course, is just 1. So here on the other side, the derivative of x is just 1. Now be careful. Remember that y equals f inverse of x. So y prime is actually what we're looking for. Y prime is exactly the derivative of f inverse right here. This is the derivative of f inverse. So that's what we're looking for. So let me isolate the y prime. So I get y prime equals 1 over f prime of y. Last step here, replace this y. Remember, y equals f inverse of x. These are the same. And I can replace the y on both sides with the f inverse of x. So I've replaced this y right here with f inverse of x, and this y right here with f inverse of x. And you can see those on the other side that's been replaced. So that's the mathematical proof. And I hope you understand the math, but at the end of the day, you really need to know the result. So here's the result one more time. If C equals F inverse of A, so if C is the output you get, when A is the input for F inverse. Another way to say C equals F inverse of A is that F of C equals A. Then the derivative of the inverse of F at A, so this is the derivative of the inverse, equals the reciprocal. This is the reciprocal of the derivative of F at C. And so, it kind of looks like we pulled out the reciprocal. We pulled that out. And when we pulled it out, the A reverted to a C. And remember, A and C are related. They're not random. A and C are connected pairs. They're inputs and outputs, depending on, if you're looking at F or F inverse, they're inputs and outputs. So here in this formula, in my mind, I always kind of think, oh, you pulled out the inverse. And when you pulled out the inverse, the A flipped to, the other number that A is associated to. A and C are connected because of the function F or F inverse. So let's do a quick example. And, it'll take a little bit of time for you to get used to the notation and for you to get used to this idea. It's a little bit tricky. Okay, so if that previous slide is like it's making you feel a little weird, that's totally normal. If you haven't seen this before, it's going to be a little strange, and it's okay. The more we work with it, the better it gets. Okay, so just take it slow. Don't worry. So here, we're asked to find, there's a derivative problem, we're asked to find the derivative of the inverse of f at -1. Make sure you understand the notation. This -1 is an inverse. This other -1, that's in the domain of f inverse, or that's in the range of f. Okay, so I want the derivative of the inverse at the number x equal to -1. So here it's really important that you realize that this problem, we're meant to use the theorem. Here, don't try to find the inverse. In this case, it's very difficult, if not impossible, to solve this equation for x. So this equation right here, y equal to x cubed minus 3x squared minus 1, it may be impossible to solve that for x. So here the thing not to do is to try and find the inverse, take its derivative, and plug in a -1. In theory, that's correct. In practice, that's not going to be very, practical. So here we're going to use the theorem instead. For the theorem, I need two things. I need the derivative of the function, and I need to figure out what f inverse of -1 is. And we'll rewrite this equation. Instead of trying to figure out what, if f inverse of -1 equals a number, then we know f of that number should equal -1. So we'll reverse this equation and solve that equation for -1. So let me just make one comment here. You don't have to do this, but for a mathematically complete presentation, I also proved the function was 1-to-1. How did I do that? I took the derivative and I factored out and I showed that the derivative is always positive if x is greater than 2. And that's the domain restriction here. So if the derivative is always positive, that means the function is always increasing. If you look at the graph of the function, it always goes up if you look at it left to right. So if the function is always increasing, it's going to pass the horizontal line test, and so it's 1-to-1. You don't have to do this part, but I do want you to understand the math I used here. By showing that it's strictly increasing, we can show that it satisfies the horizontal line test and is therefore 1-to-1. So it does have an inverse, so it does make sense to ask about the derivative of the inverse at -1. So here's the formula from the theorem. I've got the reciprocal of the derivative evaluated at f inverse of -1, just evaluated at this number, f inverse of -1. So now let's find f inverse of -1. That's the only part we need to find. Let's find f inverse of -1. So here's where we're going to reverse the equation. So first I name it, just call f inverse of -1 something, just name it something. So here I said, let C equal f inverse of -1. And now I'm going to reverse the equation. Here, just, to bug you about it one more time, apply f to both sides of this equation and convert this equation. If we apply f to both sides, on the left-hand side here, f of c is just f of c. On the right-hand side, f of f inverse of -1 gives me back -1 since we're dealing with inverses. Now I plug in for f of c because I know the function f of x. So here I can plug in c for x, and so f of c is c cubed minus 3 squared minus 1 is equal to -1. And now I'm going to take this -1 and move it over to the other side. It becomes positive. 1 minus 1 is 0, so I get the equation c cubed minus 3c squared equals 0. I factor out the common term, and I get that c is either 0 or 3. But because of the domain restriction here, remember c is in the domain of the function f. And the function f has a domain restriction that its inputs have to be greater than 2. So here c cannot be 0, c has to be 3, because that's the only number that's greater than 2. So I've discovered, what have we discovered? Well, we figured out that c is equal to 3, but c was what we were calling f inverse of -1, right? c was exactly f inverse of -1. So I've found the number to plug into the formula here. I've found this expression right here, which is f inverse of -1, we know that's a 3. And I know f prime, we found earlier, we showed f prime of x was 3x squared minus 6x. So finally, I just use that, plug it in, do the math, I get the derivative is 1/9. So what the derivative of the inverse at -1 is 1/9. So like I said, this is tricky, and you should look at this a couple of times. This is definitely tricky. Okay, we'll of course talk about this a lot more some more. This is just the first example. We'll do more. This ends our discussion of section 5.1, so I'm going to stop right here.